So here we are going to continue where we had left off from our first lecture. And if you recall at the end of our first lecture where we had been discussing significant figures, our next step was then to work on some practice exercises. So if you have not done in-class exercise number 1 at this point, I would recommend that you pause the video and go back, spend a little bit of time working on those exercises, and then you can come pick the video back up here. So now that you've completed those, we're going to go through, not every single one of them, but I'll go through a variety of these questions, and then I'll post the solutions to the rest of these. So our first question here asks us, what is the length of the red line drawn in? And we're looking at this line here. Now, the key here is that on the ruler being used here, we have clear graduations, clear markings for every 1 centimeter. And we can also see that this line is greater than 5 centimeters, but less than 6 centimeters. So whatever our answer is that we're going to write in here should fall somewhere between 5 and 6 centimeters. Now, we do have graduations every 0.5, and clearly we can see that it's actually a little bit above 5.5. But because we don't have graduations every single tenth, we can't estimate digits any further. So we're going to find that this is somewhere between 5.5 and 6 centimeters, and we might say that the line here is around 5.7 centimeters. Now for the next one, where we're looking at the length of the pencil, you can see that our ruler here does have both the centimeters drawn in, but we also have markings for every 1/10 of a centimeter. That's what the small lines in between there are. And because we can see clear graduations for every 1/10 of a centimeter, then because of that, we can then estimate 1 decimal place further. So this pencil looks like it's right almost exactly at 9.5 centimeters, but again, because of the accuracy we can show, we would add in a 0 to show that we are estimating the 100th place. And as always, we have to make sure we put a unit in. Any number that we ever put in that has no unit doesn't really have any meaning. On our third one, looking at volume. Now, some of you asked me about this and said, isn't it kind of strange that the volume numbers are going down from the top as opposed to going up like they would in a graduated cylinder? And that's because this is coming from a piece of glassware known as a burette. In a burette, they actually go in this direction. Again, as with the ruler above, we have clear markings every 1/10 of a milliliter. So we can see it's somewhere past 24.1 centimeters or milliliters, but doesn't quite go all the way to 24.2 milliliters. So therefore, again, we're going to estimate that last digit. It will come in somewhere between 24.1 and 24.2. And to me, it looks like it's maybe a little bit over halfway between them, remembering that we always measure by the bottom of the meniscus when we're looking at a liquid, and we would record that as 24.16 milliliters. All right, now if we go on to a couple of the math problems that were given, recall that we have different rules for both multiplication and division, and those rules are very different from the rules for subtraction and addition. So I'm going to do a couple of those problems, but we will get plenty of experience using these types of significant figure calculations, because for pretty much the rest of the course, anytime we do calculations, we have to take our significant figures into account. So if we look at question 6, In question 6, we have three numbers to add: 37.76, 3.907, and 226.4. So we can start by adding these. If we're going to do that in this way, helps to make sure we always have our columns lined up correctly. And we get 268.067. But what we have to take into account when we're doing addition and subtraction are the number of decimal places. So our first number here has 2 decimal places. Our second number has 3 decimal places, and our last number has only a single decimal place. So that means when we do any rounding in our answer here, we round to the least number of decimal places, which is 1, or the 10th place. And so our answer of 268.067 will get rounded to 268.1. If we go down to the next problem, number 7, 319.15. Now subtracting 32.614. So again, we should start by just doing the problem exactly the way it's written. We don't do any of the rounding until we get to an answer. So when we do that, we get 286.536. But again, we have to take into account the appropriate number of decimal places, which in this case is 2 in the first number and 3 in the second number. That means we need to round to just 2 decimal places, giving us our final answer of 286.54. All right, I'm going to jump down to problem number 10. That's our first multiplication problem. 2.02 times 2.5. Again, we can start out by just entering it directly into our calculator and get the answer that comes out that way. If we do that, we get an answer of 5.05. But we're dealing here with 3 sig figs in the first number, 2 sig figs in the second number. That means, because this is a multiplication problem, the decimal places don't matter. It's the number of significant figures. We need to round to the smallest number of significant figures here, which is 2, and that gives us 5.1. Finally, I will do question number 11. Question number 11 is a division problem, but it works exactly the same as multiplication. So 600 divided by 5.2302. Again, we can put that into our calculator. We get 114.718366, and this one keeps going. Again, though, we're going to go by the least number of significant figures, which is 4 in our first number versus 5 in our second number. That means we need to round to 4 significant figures in our answer, and we get 114.7. So there we have some explanations for how we work through some of these problems. Again, as I said at the beginning, I will post the solutions for the rest of them on Blackboard, and you can let me know if there are any questions. However, from here, we're going to go on to our next topic, which we already talked a little bit about during our previous lecture, and that's the idea of unit conversions, which we will do using a process known as dimensional analysis. So, dimensional analysis is a process by which we can convert from one unit to the desired unit. Now, sometimes we're going to be able to do that in one step, but sometimes it's going to take multiple steps to do that. But the key here is that just as you can with numbers, for example, if you have a multiplication problem that involves a fraction, 3 times 6 divided by 3. We know that if we have the same number in the numerator that we do in the denominator, that we can cancel these out. Well, the same thing is true for units. If we have the same unit in both the numerator and the denominator, as we do here, where we have grams times milliliters divided by milliliters, our milliliters will cancel, and we're left just with grams. So we use this process to come up with the way that we want to convert. And so units are converted using appropriate conversion factors. These conversion factors give us a relationship between the current unit and the unit that we need. Now, why can we do this? Well, let's consider a situation where we're converting from milliliters to liters. We know that 1 liter is equivalent to 1,000 milliliters. So we could set up a conversion factor in one of two ways. 1 liter over 1,000 milliliters, or 1,000 milliliters over 1 liter. And we would pick which one of these we use depending on the direction that we need to go. The important thing to remember though here what's important to remember is that these conversion factors, because the numerator and denominator, while they might be different units, the numerator and denominator are equal to each other. Because they're equal, this is the same thing as multiplying by 1. And because we know multiplying by 1 doesn't change the value, the only thing we're changing in a unit conversion is the unit itself. So how do we do something like this? So we can go in a series of steps. Start by listing the unit that's given. Then we need to find the unit that we want, and then we find appropriate conversion factors to get us there. So let's try it by doing the following. Let's say we wanted to know how many inches are in 1 kilometer. Now, on an exam, there are certain unit conversions I'm going to expect you to know, and then there's certain conversions that I would give you. So recall last time in class, we went over a series of metric prefixes: giga, mega, kilo, deci, centi, milli, micro, and nano. Any of those I'm going to expect that you would be familiar with them. Any unusual unit conversions? For example, anything that deals with a British system unit or that deals with a unfamiliar prefix, I'll give you something that would help you to get there. So in this case, the unit conversion I might give you to help is that 1 inch is equal to 2.54 centimeters. That will give us enough information to convert from kilometers to inches. Now, we need to know our prefixes, and hopefully we know that kilo means 1,000, whereas centi is 1/100th. But we might not know easily how to convert directly from kilo to centi. We may need some help getting from one to the other. So when we're dealing with different metric prefixes, it's often helpful to convert first to the base unit. So what will that look like? So here we're in kilometers. We're trying to get to inches. So we can go from kilometers, and we know based on the information given that the easiest way to get to inches is to go through centimeters. So now we have two metric units, kilometers and centimeters. We need to get from one to the other. And we can do that by going through the base unit of meters. So now that we know how we need to do this, let's go ahead and do this question. How many inches are contained in 1 kilometer? So 1 kilometer, we're going to convert first to meters. Now we know that there's 1,000 meters in 1 kilometer. The only thing we have to figure out is when we set up our conversion factor, are we going to set this up with kilometers on the bottom or meters on the bottom? Now, since kilometers here are already on the top, we want it to be able to cancel out, and so we will put kilometers on the bottom. Now, our kilometers cancel, and we will be left with meters. So we get 1,000 meters. Another way to think about this, though, is also what would have happened if we had flipped our conversion factor the wrong way. Then we would have had 1 kilometer times 1 kilometer over 1,000 meters. The first thing we can see is that our units don't cancel. We would have ended up with kilometers times kilometers over meters. And that doesn't really make sense as a unit. The second thing is we would have gotten an answer of 0.001 up here. And one of the things we should always think about with any calculation we do is we should always think about whether the answer we get, does that answer make sense? And given that we know that a kilometer is much, much larger than a meter, it wouldn't make any sense for our number to have gotten smaller. So one of the stories I often tell is a couple of years ago I was giving a quiz in this course, and I gave the students the length, the radius of a carbon atom or an iron atom, and I gave it to them in nanometers, and I asked them to convert that to feet. And what happened was that I got a number of answers where the answer that was given as 200 feet. And for a lot of those students, if they had stopped and said, does that answer make any sense? Think about what that answer is saying. In that case, they gave an answer that said the size of a carbon atom is 200 feet. And so at that point, hopefully you would realize, wait, the answer I'm giving doesn't make any sense, and I've made a mistake somewhere. All right, so let's continue on with our work here. We've gone from kilometers to meters. Now I'm going to go from meters to centimeters. So we know that there's 100 centimeters in every meter. We're going to put centimeters on top, and now meters will go on the bottom because we want meters to cancel. That'll leave us with centimeters. But we don't need to stop and calculate after each step. You certainly can, and when this is new to you, you may find that to be very beneficial. But eventually, we're just going to string one conversion factor together after another. So now to go from inches to centimeters, I need to use my inches to centimeters conversion. Now centimeters will go on the bottom, so 2.54 centimeters on the bottom, 1 inch on the top. And so from here, this just becomes an arithmetic problem. And if I calculate this out, I find that 1 kilometer contains 39,347 inches. Are we done? Almost. What else do we need to do at this point? Well, our starting number, 1 kilometer, that only contains one significant figure. Therefore, the answer we got here should also contain only one significant figure. And so our 39,347 inches should round to one significant figure, or 40,000 inches. Now, at this point, I'm going to stop this file and continue with the next video file. We're going to do some more practice in the next file. I'm just going to break this up so that the size of these files does not get to be too large.